So thank you all for joining for this new reading group session of ContinualAI. Today we have the pleasure to host Ahmet Iscen, that is going to present his recent paper, Memory Efficient Incremental Learning Through Feature Adaptation. So thank you, Ahmet, for being with us, and the stage is yours.
Thank you for inviting me. My name is Ahmet Iscen. I'm a research scientist at Google Research in Grenoble, France. And I will present to you our work titled Memory Efficient Incremental Learning Through Feature Adaptation. This is work in collaboration with Jeffrey Zhang, Svetlana Lazebnik, and Cordelia Schmidt. So I will first talk briefly about the incremental learning problem and give a little bit of background. In a typical incremental learning setup, we are given a different set of classes at each task. And at a given task, we don't have access to the data that we had seen from the earlier tasks. However, during the inference, the test set contains images from the current and earlier tasks. So the goal is not to forget the information from the earlier tasks while correctly classifying the classes seen in the current task as well. And again, just to show a toy example of an incremental learning problem. So let's assume that we only have two classes in task one, and these are the two classes that we have. So we, like any other classification problem, we train a CNN using the training set from these, which consists of these two classes. We learn our model, and we test it with the images that come from the same two classes. However, in incremental learning setup, after task one, we lose access to the images in the training set after task one. So that means that we don't have access to the images from classes 1 and 2 anymore. And at task 2, we are given a new set of classes 3 and 4. And we need to continue training our model, our CNN model, to learn the patterns in these new set of classes. However, the test set still contains images from classes 1 and 2 that we had seen in task 1. So we should also retain the information from task 1 while learning the model in task 2. So a well-known paper by Carl, which you probably heard about, addresses this problem with what is called image-based rehearsal for incremental learning. So what this does is essentially it preserves a few instances from all classes at each task. And it has shown to significantly improve the accuracy of incremental learning problems. So just to go back to our toy example again, this is how our training set would look like with iCarl at task 2. We have the full set of images from classes 3 and 4. Those are the images corresponding to the new task. But we also keep a small number of images, in this case only a single image, per class from the classes we have seen in task 1. And when we train the model using the images from the new classes as well as the preserved images from the old classes. So we built our motivation for this work on top of iCarl's general idea. iCarl stores images from the previous tasks, raw images, and these raw images can be pretty expensive to store, especially for large-scale scenarios involving millions, maybe billions of images. And to make sure that the memory requirements are scalable, in that case, we need to lower and lower the number of images that we preserve from the old tasks as the number of images increase. And this hurts the accuracy because we store less and less images now from the previous classes. So in order to alleviate this problem, we asked the question, can we store more data points with less memory footprint? And in fact, our idea is to store feature descriptors instead of images. So feature descriptors, as we know, they are low dimensional representations of raw images with a given CNN. So CNN, let's say, learned CNN takes a raw image as the input, and it projects it to a much lower dimensionality and outputs a single feature descriptor of low dimensionality, which should represent the image in a way which is easily classifiable and discriminative. So our idea is to store feature descriptors instead of images, because if we can do this, then it's much scalable to store many feature descriptors instead of raw images. And so this is another toy example of how our framework would work. So let's say, again, at task 1, we have classes 1 and 2. So now instead of actual raw images, we have feature descriptors. So in this figure, triangles and circles shown here, they actually correspond to feature descriptors in a toy 2D space, two-dimensional space. And with the learned CNN, we actually have these nice feature descriptors that are very separable. So just like with those two classes, we can learn a very nice classifier. However, at task 2, we now have a new set of classes 3 and 4. And we continue training the network, the CNN network, with these new set of classes. After training the network, we extract features for these new set of classes 3 and 4, with the new network. And they are not compatible with the features that we extracted from classes 1 and 2, because the CNN network updated its parameters. So the feature extractor is not the same as the one that we use to extract features of class 1 and 2. So the collected set of features from these 4 classes are not compatible with each other. So for example, here we saw that we see that the features of classes 1 and 3 are close to each other, even though they probably shouldn't be, because they probably represent different things. And to address this problem, what we propose is a feature adaptation network. This is basically a function which maps the features of the old feature space to the features of the new feature space. So if we can learn such function, such feature adaptation network, we would apply it to the features from classes 1 and 2 that were preserved from earlier tasks, and map those features to the new feature space, where they would be separable again from the features of the new classes 3 and 4. And if we can achieve this, we would have this nice feature space where the features of all classes again are far away from each other, and we can classify these features. So I will now show you how our complete framework looks like for a given task. So at a given task, we use the images from this task to extract 2 sets of features for the same set of images. The first set of features are extracted with the old model, old CNN, and the new set of and another set of features are extracted with the new model. So what are these old and new models? Old model is the CNN model, which we save and fix at the end of the previous task. So as we were beginning the current task, we've saved a copy of the model, which was output at the end of the previous task, and we fix it as the old model. The new model starts from the old model, but it continues to train with the images of the current task. And once the training is complete, we take this model to extract the new model features. At this case, at this point, we have 2 sets of images corresponding to the same. We have 2 sets of features corresponding to the same images, but these features are in different feature spaces, extracted with 2 different CNN models. Then we train our feature adaptation network. So this feature adaptation network basically learns to map the features from the old model space to the new model space so that they are compatible. Once this feature adaptation network is trained and learned, we apply it to the previous task features in the memory. So those are the features that we keep accumulating from the previous tasks in our memory. And as another task comes along and the CNN network changes, they need to be adapted to the new feature space so that they can be used with the new class features. So we adapt them to the new feature space with feature adaptation network, update the memory, and now that the features, the previous task features are adapted to the new feature space, we can combine them with the features from the classes of the new feature space, new task, and use them to train a feature classifier for classification. So in our case, the feature classifier is a simple linear classifier which is learned on top of the features of the memory. How do we train this feature adaptation network? What it looks like? So essentially, it's a two-layer multi-layer perceptron with a ReLU in the middle for nonlinearity. And we train it with the following loss function, which is shown here. So this loss function, it receives three inputs. V bar, which is the feature descriptor of an image extracted with the old model. V is the feature descriptor of the same image extracted with the new model. And Y is the class label for that image. And we actually have two different loss terms. So the term, the loss term on the left, it encourages the feature. It encourages the new adapted feature to be similar to the ground truth feature. So V here is the ground truth feature. It's the feature which is extracted with the new model. And can you see my mouse? So, oops.
Yes, we can see it.
So this is the feature adaptation network function which we are learning. So this is the function which is learned in this process. And when we input V bar to this function, we want its output to be as similar to V as possible, because this is the mapping that we want to learn. And we also have a second loss term, which is simply a classification loss term. So here, again, we take the output of the feature adaptation network with V bar as the input, and we want to make sure that it is classified to the correct class. And here, the classifier, which is here, GW, it's a fixed classifier, which is simply taken from the last layer of the neural network, which was learned in this task. So it's just to make sure that the adapted features do not get classified to the wrong classes. So after adapting these features, we can now save them in our memory. But of course, we don't want to save all the features of all the images of a given set of classes, because even though it's much more scalable to store features instead of images, if we store all the features, at some point the memory is going to explode. So we should only choose a subset of features to store in the memory after each task. And the subset selection is done the same way that iCarl does its subset selection. We use an algorithm, greedy algorithm called herding. It's an iterative algorithm, and at each iteration, we find a class mean for a given set of features, and we take the feature that is the closest to the class mean, and then we update the class mean without the selected feature and select the next closest feature, and so on until we reach the number of features that we want to select in this subset. So now I will describe our experimental setup. We run our experiments in 3 data sets: CFAR 100, ImageNet 100, and ImageNet 1000. ImageNet 100 is basically a smaller subset of ImageNet 1000. We use ResNet 32 for CFAR 100 dataset. It outputs 64-dimensional feature descriptors. We use ResNet 18 for ImageNet datasets. It outputs 512 feature descriptors. And we report the average incremental accuracy metric. So this is basically the average of accuracy values recorded after each task. And we also propose a hybrid variant of our method in our experiment. And this hybrid version, we basically preserve both images, a very small number of images, along with feature descriptors. So here I show experiments where we show average incremental accuracy versus memory footprint in megabytes. So we vary the number of images in our curl to have different memory footprints, and we vary the number of features for our method to have memory footprints. For ours hybrid, we fix the number of features per class. So for the case of ImageNet datasets, we preserve 250 features per class, and we vary the number of images to have different memory footprint data points. So here we see that we can achieve better results compared to image-based rehearsal methods with much less memory footprint, especially for higher M. And what is M? M is the number of classes per task. So for example, ImageNet 100 has 100 classes. At each task, we have 10 classes. So we end up having 10 tasks to get through the entire data set. And when the number of classes per task is higher, our hypothesis is that the network learns better feature representations, and it's easier to adapt these feature representations between the tasks. And in such cases, we can achieve a much bigger improvement compared to image-based rehearsal methods like iCarl. And even for a smaller M, such as M equals 5 in ImageNet 100 or M equals 50 in ImageNet 1000, we can still achieve a better accuracy compared to iCarl with the hybrid variant of our method, which preserve a small set of images, very small number of images with feature descriptors. So using the same memory footprint, the accuracy is better. And so, on the other hand, our gains are not so impressive on CFAR 100. This is sort of expected because CFAR 100 has very low image resolution in the dataset. So the dataset images for CFAR 100 are 32 by 32 resolution pixels. So we don't actually gain much by just preserving feature descriptors instead of images in this case, because images don't take so much space to begin with. So in such case, the gains compared to iCarl are not impressive, and we don't have stronger gains. So we know, like we saw that we achieve better accuracy with feature adaptation, but how accurate are these adapted features actually? So it helps the accuracy, but how accurate are they? So we defined adaptation quality metric as the cosine similarity between adapted features and real features if we had access to those images, to the corresponding images. So in practice, we don't have access to those images in incremental learning setups, images from previous tasks. However, for the sake of this experiment, we just go and grab those images at each task and extract their features and measure how accurate the adapted features are compared to the real features. And we basically show different variants of this experiment. So the solid lines show the comparison of adaptation quality with respect to the features from the previous task only. So this measurement basically shows how accurate the adapted features are between two consecutive tasks. And the dashed lines show the feature adaptation quality of the images that we saw in the first task, and how the feature adaptation quality evolves over training, over different tasks. And P, another variant, the P is the number of preserved images. So we see if we want to see if we preserve 50 images per class, for example, if this helps with feature adaptation. So we also report that. And so the solid lines show us that the feature adaptation quality actually gets better as the training evolves. So this shows the feature adaptation quality between two consecutive tasks. And again, our hypothesis is that as the training evolves, network starts to learn more and more generalized feature representations, more robust feature spaces. So this helps with the feature adaptation as well. Dashed lines go down as the training evolves. This is also expected because we are more likely to lose information, and the features are more likely to drift as the training goes on. However, still at the end of the training, after 10 tasks and seeing 100 classes, the first 10 classes from task 1, their features are still remain around 0.8 cosine similarity compared to the ground truth features. Adapted features are still like in average 0.8 similar to the ground truth features. And this is even higher if you also preserve 50 images per class. So then this goes up to more than 0.85. So to conclude, we propose to preserve features instead of images for incremental learning. And we apply a feature adaptation method to preserve features in order to make them compatible as the network evolves during training between tasks. And our experiments indicate that we can achieve higher accuracy with less memory footprint compared to the image rehearsal methods such as iCarl. And the paper is available on arXiv. It was also presented at this year's DCCV. And if you have any questions, I would be pleased to answer.
Thank you very much, Ahmet, for your very interesting presentation. I think that these kind of ideas of trying to use replay in the latent space is becoming more and more shared, at least as a view from many researchers in continual learning. So it was an idea very much on point, I believe, also for the future of this field. I have a little question for you just to break the ice and to start the discussion. Surely using these very compressed embeddings for replay, you reduce a lot the memory consumption, and as you discussed, this method is very memory efficient. But if I understood correctly, you have to train the adaptation network for every step, or you keep it fixed somehow. I may have missed this point.
So the adaptation network is trained after each task,
okay.
But we don't save the adaptation networks that were trained from earlier tasks. So let's say after task 2, we have features from task 1, right? Which lie on different feature space. So we train an adaptation network. We adapt those features to the new feature space. We update the memory, and we move on. And we throw away the adaptation network that we learned. And then at the end of task 3, we do the same thing again.
Yeah, cool. So my question was, did you see any limitations, especially in terms of computational efficiency to this approach? Because what I can see from here is that you have to train the feature adaptation network for every step, and also the feature classifier. Let's say, I mean, since you're changing the features also from previous examples that you learned in the past, you have to essentially relearn a classifier, if I'm correct, and then you have also this earning procedure for selecting examples. So these three components, have you seen they impact the computation? I mean, the computational overhead, or they are kind of manageable even for large-scale experiments that you run, like for ImageNet?
So they are very manageable because, like, the feature adaptation network is basically a 2-layer MLP. So it's very easy to learn compared to the actual CNN network that we are optimizing. So that's actually the bottleneck by far. So the adaptation network is a 2-layer MLP, and the classifier is just a linear classifier. So, and like when we learn these things, we don't have to re-extract features. So we extract the features once and just, you know, use them to learn a single layer or 2 layers. So those parts of the framework are actually quite fast to do. Again, like, as we don't have to re-extract the features. So that's the key point in terms of scalability. And the CNN takes the most amount of time. So that's where the bottleneck comes from.
Cool, thanks. Do you have any more questions for Ahmet? Well, I don't think that there are any more questions. So thank you so much, Ahmet, again, for your presentation. And I invite you all to join again the next ContinualAI Reading Group session next Friday, kind of the same hour at 5 p.m. chess time. So thank you so much again for joining. Thank you, Ahmet, and I'll see you next time.
Thank you for inviting me, and see you next time. Have a good day.